Okay, let's dive into this. Welcome to today's explainer. Class, today we're decoding the universal language of matter, and we're going to do it by taking a journey through a place you probably visit every single day, a typical busy family kitchen. Whether you realize it or not, every time you cook, you're literally doing chemistry. So instead of looking at random bubbling beakers, we're going to break down the exact fundamental rules of how substances interact just by looking at our food. By the end of our lesson together, you'll be able to read the hidden recipes that dictate how our physical world operates.
Here is our menu for today's lesson. Section 1, the skeleton of an equation. Section 2, balancing the chemical equation. Section 3, 5 types of reactions. Section 4, oxidation and reduction. And finally, Section 5, chemical energy changes. Let's get cooking.
Starting right at the beginning with Section 1, the skeleton of an equation, decoding the basics.
At the heart of it all is the chemical reaction. Simply put, this is a process where substances undergo a transformation to form new substances with entirely different properties. Think of baking a cake in your busy family kitchen. You aren't just stirring things around, you're taking raw ingredients, applying heat, and rearranging them at the microscopic level into a completely new, delicious substance. It's a literal transformation of identity.
And this brilliantly illustrates a simple left-to-right journey to capture that transformation. On the left side, we have our reactants. In our kitchen, think of these as your raw starting ingredients, like flour, eggs, and sugar. The arrow? Well, that's the cooking process itself, the actual transformation taking place, leading us to the right side, the products. That's your brand new substance, the freshly baked cake. It's a clean, universally understood map of matter changing from one state to another.
Now, chemists also need to know exactly how these ingredients exist in physical space. These 4 tiny state symbols act as crucial adjectives in our chemical language. A lowercase s tells us a substance is a solid, like a cold stick of butter. An L stands for liquid, like cooking oil or tap water. A G means it's a gas, like the steam rising from a boiling pot of pasta. And AQ stands for aqueous, meaning the substance is completely dissolved in water, just like the sugar stirred into a morning cup of tea. Adding these little tags gives us a perfect, high-definition picture of our recipe.
Let's move to the grammar of our kitchen. Section 2, balancing the chemical equation, the unbreakable rule.
Mass can neither be created nor destroyed. This is the law of conservation of mass. And class, it is absolutely unbreakable. Think about what that actually means for us. The universe is a perfect, flawless accountant. When you bake, you cannot magically conjure up new atoms, and you definitely can't make existing ingredients vanish into thin air. The total mass of the raw ingredients we start with must be perfectly equal to the mass of the cooked food, plus any steam or gases that escape during baking.
Let's look at exactly how this plays out, treating it just like scaling a recipe so absolutely nothing is left over. Look at that unbalanced equation for water. We start with 2 hydrogen atoms plus 2 oxygen atoms, but the resulting product, H2O, only has 1 oxygen. Well, that violates our conservation law. An oxygen atom can't just disappear, right? So we have to scale our recipe to balance it. By doubling the hydrogen we start with and doubling the water we produce, we fix the math. Now we have 4 hydrogens and 2 oxygens going in and exactly 4 hydrogens and 2 oxygens coming out. Our recipe perfectly obeys the absolute rule of the universe.
Now that we know how to properly balance our ingredients, let's explore Section 3, 5 types of reactions, the genres of matter.
Let's quickly walk through these 5 different ways things can cook. First is combination, where 2 or more reactants combine to form one single product. Then we have decomposition, the exact opposite, where a single reactant breaks down into 2 or more products. Next is displacement, where a more reactive element pushes out a less reactive one. Then we step it up to double displacement, which is kind of like an atomic dance, where 2 compounds actually exchange their ions to form entirely new compounds. Finally, we have combustion. Class, this is literally your gas stove turning on. A hydrocarbon reacts with oxygen to release heat and light, giving us the fire we need to cook. And a quick kitchen safety rule while we're at it, always keep flammable items like paper towels far away from these combustion reactions and never, ever leave an active stove unattended. Moving right along to Section 4, oxidation and reduction, the electron exchange.
Oxidation is defined as the gain of oxygen, or the loss of electrons. Reduction is the exact opposite. It's the loss of oxygen or the gain of electrons. It's kind of like a cosmic game of tug of war, where one substance is giving something up and the other is taking it in. In our kitchen, when you slice an apple and leave it on the counter, it turns brown. That browning process is actually oxidation.
The apple's flesh is reacting with the oxygen in the air, losing electrons in the process. The exact same concept applies when we're beautifully browning a piece of meat.
So the crucial point is this. Remember, class, this is a perfect exchange, so these two processes never ever happen alone. You cannot have something lose an electron unless there is something right there waiting to catch it. Both oxidation and reduction must happen simultaneously in what we call a redox reaction. It's a perfectly balanced transaction every single time.
And for our final lesson today, Section 5, Chemical Energy Changes Interacting with the Surroundings.
In our kitchen, reactions are all about heat transfer, often relying on simple kitchen tools like a heavy cast iron pan to move energy around. Here we see the stark difference between energy leaving a system and energy entering it. Exothermic reactions release energy into the environment. Think of your gas burner combusting, releasing a massive amount of heat to warm up that heavy pan. Endothermic reactions, on the flip side, actively absorb energy. When you drop a solid cube of cold butter into that hot pan or crack in a raw egg, those ingredients are undergoing endothermic processes in that moment. They are actively absorbing the heat energy from the pan to break their bonds, melt, and cook.
Chemistry isn't just a bunch of boring formulas in a textbook. It's the busy, dynamic family kitchen cooking up the physical world around us. Class, I want to leave you with this final thought. The next time you see ice melting in your glass on a warm summer day, or you watch food browning in a hot pan, ask yourself, is this process absorbing or releasing energy? Start looking for these invisible recipes in your everyday life. Thanks for joining me for today's Explainer. Class dismissed.